In the last lecture, we learned that although the standard Big Bang theory was amazingly successful, it was seriously lacking in its ability to explain several fundamental properties of our universe. That its geometry is Euclidean, that it's smooth on the largest scales, and that it was born slightly lumpy. We also figured out that the primary reason the standard model was unable to explain these properties was because its expansion began infinitely fast and then rapidly decelerated. And it was these characteristics that caused the problems. We also learned that a period of accelerating expansion could solve at least the flatness and smoothness problems. So we begin this lecture ready to look for ways to introduce an accelerating expansion into the early universe. Now, historically, the first people to come up with an actual mechanism to generate this acceleration were, independently, Alexei Starobinsky in the former Soviet Union and Alan Guth in the United States, both around 1980. And it was Guth who introduced the term inflation to describe the process. Now, since then, there's been a huge amount of work in this area, and the whole theory has come a long way since those first ideas of Starobinsky and Guth. So today, cosmologists work with what's called the inflationary hot Big Bang theory. It's basically the standard hot Big Bang theory, but with inflation added on as a launching mechanism. Now, adding inflation doesn't alter any of the great successes of the standard theory. It simply gives a very plausible starting mechanism for the expansion. And as a bonus, it also solves the problems we talked about last lecture. Now, I want to stress at the outset that the inflation part of the inflationary hot Big Bang theory does not yet have the same robust status as the hot Big Bang part. It's thought that something like inflation very probably occurred, but the details of exactly how it happened and when it happened are still rather unclear. So you want to think of inflation as an extremely promising framework, but it's not yet been filled in. Now, having said that, the observational support for inflation keeps getting stronger and stronger, and there are some crucial tests coming up in the near future. So, with this cautiously optimistic introduction, let's have a closer look at the nature of inflation. So the first question is, what might cause an accelerating expansion? Now, we've already met something that can do just that. It's called dark energy. Remember from lecture 12, the key property of dark energy is that it is a vacuum energy, which doesn't get diluted with expansion. And this leads to the remarkable property of it falling outwards. And with nothing to stop it, the expansion just keeps going, getting faster and faster, accelerating. So perhaps the accelerating expansion we need in the early universe is something similar to dark energy. Now, today's dark energy accelerates extremely gently for the very simple reason that the energy in the vacuum is extremely tiny, so it doesn't fall outwards very fast. What we need for the early universe is a much more potent version of dark energy, one which has a higher vacuum energy. It must have more mass in its space. Now, to figure out what energy or mass is needed for this early vacuum, we need to know when inflation occurred. Remember, the standard hot Big Bang theory is fine back to at least 1 microsecond. So we need to put inflation sometime before that. So just to get going, I'm going to be specific and choose 1 picosecond. That's 1,000th of a nanosecond, when the density was about 10 to the 24 tons per cubic centimeter, pretty high by human standards. Now remember, in the standard model, this density drops rapidly as the universe expands. But now imagine that the vacuum at that time somehow acquired a similar density. Perhaps it got excited in some way by all the particles. we now have a vacuum density of 10 to the 24 tons per cubic centimetre. And because that density doesn't drop with expansion, it changes the expansion enormously. This graph, which is essentially from Lecture 12, shows how radiation and vacuum-dominated universes expand extremely differently. The radiation universe starts fast and decelerates with size proportional to the square root of time. And the vacuum universe starts slowly and accelerates with its size doubling, then doubling, then doubling again. Its size grows exponentially. So let's put in some numbers here and allow these two universes, starting at 1 picosecond, to expand for just 100 picoseconds. So the radiation universe, which grows with the square root of time, gets 10 times bigger, because 10 is the square root of 100. Now, to figure out how the vacuum universe grows, we need to know what is called its doubling time. That's this little interval of time here, the time it takes to double its size. Now, to find out what that doubling time is, I'm going to show you an extremely handy little formula that applies to almost all systems in which gravity dominates. The time for a system to fall, T-fall, is roughly 1 over the square root of Newton's gravitational constant g times the density of the system, rho. Now, the word fall here could mean the time for the system to collapse under its own gravity. Or it could mean the time for something to orbit the system. Or in the case of a vacuum universe, it could mean the time for it to fall outwards and double its size. Here are some examples just to get the feel for this. For systems with water density, T-fall is about an hour, which sounds about right because it takes about an hour for satellites to orbit the Earth, and the Earth is only a little bit denser than water. The much lower density of today's universe means it would collapse in about 10 billion years if we let it go from stationary and it contained just matter. But since it actually contains mainly dark energy, it will in fact take about 10 billion years to fall outwards and double its size. Now, going to much higher density, a neutron star, which has the density of an atomic nucleus, would collapse in about a millisecond. And now we come to the density we're interested in. At 1 picosecond, the density is 10 to the 24 tons per cubic centimetre, and T-fall is in fact about 1 picosecond. This is the number we need. Our hypothetical universe falls outwards with a doubling time of about 1 picosecond. So, and here's the critical part, after 100 picoseconds, the universe's size has doubled and doubled and doubled 100 times. Now, I could just tell you what that number is, but I want to remind you just how powerful exponentials are, using this famous example of the 64 squares on a chessboard to track 64 doublings, not of cosmic size, but of rice grains. We start with a single rice grain on the first square, then 2 on the next, then 4, then 8, then 16, and so on. By the 32nd square, we have 2 to the power 31, or a little over 2 billion rice grains that fill a truck. By the 48th square, we fill a tanker. By the 64th square, we pack a mountain. And if we push on to reach 100 doublings, we have 10 to the power 30 rice grains which fill the Earth. So after 100 picoseconds, our radiation universe is 10 times bigger, but our vacuum universe is 10 to the power 30 times bigger. This is an extraordinary difference. And when you first hear it, it barely seems possible. So let me remind you what's happening. We have a region 10 to the 15 times denser than an atomic nucleus. So I think you can see that if it was made of matter, it would collapse in on itself quickly, bam, in about a picosecond. But a vacuum of the same density falls outwards at the same rate, bam. After 1 picosecond, it's twice the size. So we have 2 by 2 by 2 or 8 new regions. But in the next picosecond, each of those doubles in size, and we now have 64 of them, and so it goes. Now, unlike the inward collapse, which stops at a point, this outfall has nothing to stop it. So it keeps falling outwards, doubling in diameter, or 8 times the volume, in every picosecond. Now, normally, when we meet exponentials, in whatever context, they rarely go above a few doubling times, because they run into some limit. Economic inflation, for example, hits some fiscal policy, or bacterial growth kills its host. But cosmic inflation has no limits, because it's creating the very space into which it's growing. It's an exponential growth of space, and there are no boundaries. There's something almost Zen about this. The only thing that can grow without limit is space itself. Now, having said that, inflation must obviously stop at some point, because we know that by a microsecond, we're back in the radiation-dominated universe. So here's an interesting question. From inflation's start to finish, how many doubling times were there? What was the true growth? Well, the answer is, we really don't know. It could have been 100 doublings, like the example I just gave you. It could have been 1,000. It could have been 1,000,000. The universe could have grown in size by 10 to the power of 1 million, which utterly defies imagination. We just don't know. The only thing we can figure out is the minimum number of doublings, because we know that inflation at least has to solve the flatness and horizon problems. So let's have a look at that now. It turns out there's a very simple condition that's needed to solve the flatness problem. You need at least as much expansion during inflation as you have expansion after inflation. And it's not too hard to see why. The later decelerating expansion makes the universe less flat. So we need to start that phase so close to flat that it's still flat today. And that means we need to drive the universe towards flat during inflation by at least as much. Okay, so let's put in some numbers. Let's stick to our example of inflation near a picosecond. Then the universe expands by a factor of 10 to the 16 from then until today. So we need inflation to drive expansion by at least the same factor, 10 to the 16, which it can do in about 50 doubling times. It's really quite amazing. There are 2 expansions, each by a factor of 10 to the 16. The first takes 50 picoseconds, the second takes 14 billion years. Now, while we're talking about solving the flatness problem, let me show you this famous figure that nicely illustrates graphically how inflation flattens the universe. So imagine standing on a small, obviously curved sphere, like this chap, and then blow the sphere up huge. The expansion takes what once appeared quite curved and now makes it appear flat. Now, the reason, of course, that the final region looks flat is simply because the total sphere is so much bigger. And notice that this is also true for our universe. Because it seems flat out to our visible horizon, the total size of the universe must be very much larger. Okay, so having solved the flatness problem, let's see how inflation solves the horizon problem. And let's once again put inflation at a picosecond lasting 50 doubling times. Now, at 1 picosecond, light, or any forces for that matter, can't have travelled further than about 1 millimetre. So we expect the universe at that time to be smooth across millimetre-sized regions. Now, and this is the important part, if there is no inflation, then those millimetre regions expand by 10 to the 16 to become about the size of the solar system today. So we would expect big variations between patches of the universe separated by more than the size of the solar system, which of course is not the case. But now add an inflation of 10 to the 16, and that smooth millimetre region becomes a smooth solar system-sized region immediately after inflation at 50 picoseconds. It then grows by another factor of 10 to the 16, bringing it up to 10 trillion light-years across today, which is 700 times bigger than our visible universe. So now do you see how inflation solves the horizon problem? That smooth millimetre-sized region ultimately becomes 700 times larger than the visible universe. So of course the universe is smooth as far as we can see. Going back to the terminology of Lecture 3, inflation has just generated the cosmological principle, the fact that the universe looks the same statistically from all locations. Now, so far I've only chosen inflation at a picosecond for convenience. When did inflation actually occur? The answer is, once again, we don't know, though we do have some guesses. Here's our graph from Lecture 29 of the time against temperature for the first second. Remember, the axes are exponential, and here's a picosecond we've just been talking about. And here are the most likely times that inflation might have occurred: around 1/10 of a nanosecond near the electroweak transition, somewhat before that during the breaking of supersymmetry, or way back at the gut transition, where the strong force separated from the electroweak force. There are theories of inflation at all three of these times, but the favourite amongst many cosmologists is the gut transition, just as it was for Alan Guth's original theory back in 1980. So here are the conditions near the gut transition. The scale factor is 10 to the minus 28, and the density is 10 to the 73 tons per cubic centimetre, which gives an expansion doubling time of about 10 to the minus 36 seconds. Now, I won't go through the logic again, but you can find a similar result to what we found for inflation at a picosecond. But this time you need at least 100 doubling times to solve the flatness and horizon problems. But either way, we end up with a large, flat, homogeneous universe, just like the one we see. So this now brings us to the all-important question of what caused inflation. It's all very well me talking about dense vacuums expanding for 100 doubling times, but how could such a dense vacuum actually arise? So let's look at that now. Well, right off the bat, because inflation is occurring in the very early universe, the branch of physics that's most relevant is high-energy physics, and specifically it is quantum field theory. Now, I'm guessing you've probably not come across quantum field theory much before, so let me briefly say why it's so important. You see, modern physics views space as being filled by many kinds of fields. These fields sort of permeate everything, and they extend across the entire universe. Each field is associated with a kind of particle, a quark or an electron or a photon, for example. One way to think of these fields is that they are the knowledge embedded in space to make their specific particle should enough energy come along to create it. Now, most of these fields, for most of them, the knowledge doesn't actually weigh anything. The field has zero energy of its own. But, and this is the important part, there are certain kinds of fields that can have energy. And this looks very much like a vacuum energy. We have a quantum field filling all of space with finite energy but no particles. These fields are called scalar fields because the particles they're associated with have zero spin and are called scalar bosons. So their fields are called scalar fields. Now at the moment, no one knows which particle or which field causes inflation. So in the absence of anything specific, cosmologists simply call the field the inflaton field, meaning it's the field that causes inflation. Now, a key idea is that although the inflaton field normally has zero energy, there are certain circumstances in which it can have finite, non-zero energy. And it's during that time that the field acts like a vacuum energy, and it's this that drives inflation. Now, although cosmologists are fairly confident these kinds of fields, scalar fields, exist, what they don't quite know is how the field manages to get into its finite energy condition. There are actually 3 or 4 fairly good ideas, and I'm just going to mention one of these that's thought to occur during one of those major transitions, like the Gutt transition or supersymmetry transition. So, as the temperature drops through the transition, the inflaton field gets stuck in the pre-transition higher energy state. And for a brief time, the difference between this field energy and the falling ambient energy becomes a real finite vacuum energy. In a sense, the field sort of inherits the pre-transition ambient energy, and bam, inflation takes off. Well, although arriving at this condition isn't that well understood, once it's there, the theory of inflation has a fairly clear way to follow how the expansion proceeds. The key thing to understand is how the energy in the field evolves over time. Remember, it's the energy that determines the rate or the doubling time at which the universe falls outwards. So if the field energy is changing, then so is the expansion. So it's important to follow how the energy in the field changes. Now, it never ceases to amaze me that out of the frighteningly sophisticated math of quantum fields comes an extremely simple way of analysing how the field energy changes. It turns out to be equivalent to the following situation. Imagine a ball sitting on a hill that slopes down to a minimum. And the height of the ball represents the energy of the field. That's what's driving inflation. Amazingly, the field energy changes in just the same way as the ball rolling down the hill, with one rather odd additional feature. The whole hill is immersed in a fluid that's thick like molasses at the top, water in the middle, and air at the bottom. So initially, the ball rolls slowly because it's in the molasses. And this is the primary period of inflation. The field energy is high and almost constant, so we have rapid, almost pure exponential expansion. But soon, the ball begins to roll down the hill, picking up speed as it feels less drag from the fluid. So now, as the field energy decreases, inflation begins to slow down. Finally, with no resistance, the ball quickly rolls to the bottom of the hill, where the field energy is zero, so inflation comes to an end. Now, at this point, you may think the story is over. The inflaton field has relaxed and inflation has stopped. But there must be more to the story, for at least 2 reasons. First of all, the enormous expansion cools everything down. So we're heading for a cold Big Bang, not a hot Big Bang. And second, the post-inflation universe contains only one thing, the inflaton field, which is empty. So it looks like inflation has just produced a very large, cold, empty universe, which of course is not what we're wanting. Well, fortunately, we've forgotten something. The energy released by the ball as it rolled down the hill is transferred into all the other quantum fields in the vacuum. In other words, there is an almighty transfer of energy into all the other particles. This extremely important event is called reheating, and you can follow it on our temperature time graph. Inflation's expansion cools everything right down, but the liberation of the vacuum energy simply reheats the universe back up, pretty much to where it was before inflation started. So now the period of inflation is truly over, and it's completed its task. Inflation has launched a hot, smooth, radiation-dominated region at the escape speed, and from then on, we simply move into the whole detailed story of the standard hot Big Bang theory. Inflation has provided the crucial launching mechanism that was so badly missing from the standard theory. Let me just review for you the main ideas of this lecture. We began knowing that one way to solve the problems with the standard model was to introduce an early period when the expansion was accelerating. What might cause this? Well, perhaps a dense form of vacuum energy, something like dark energy, but very much denser. To explore this idea quantitatively, we chose an example of inflation at a picosecond, with a vacuum density of around 10 to the 24 tons per cubic centimetre. At this density, the vacuum falls outwards, doubling in size roughly every picosecond. And after only 50 picoseconds, 50 doubling times, the universe has grown by a factor of 10 to the 16, and the flatness and horizon problems have now been solved. We looked at how such a vacuum energy density might arise. We learned that modern physics views space as filled with fields. And although these fields normally have zero energy, a subset of them, called scalar fields, can in the right circumstances have finite energy. And this behaves just like a vacuum energy. Now, at the present time, it isn't certain either when or how such a field might have acquired this non-zero energy. But there are several promising possibilities, of which the gut transition at 10 to the minus 36 seconds seems the most likely. One thing cosmologists have developed is a theory of how these quantum fields behave. They hang for a while before rapidly settling back to zero energy, giving an extended period of exponential inflationary expansion that quickly ends. Finally, in a period called reheating, the energy that's released as this field settles down to its zero state creates a hot broth of all the particles. Ultimately, inflation has launched the standard hot Big Bang, and from then on, we know what happens. Now, at this point, you may think the story of inflation is over, but it's really just beginning. So far, we've managed to generate a hot, expanding, but smooth universe. Where are those ripples that we need to form stars and galaxies? That's our topic for the next lecture.